Okay, so let's go over the solution. Initially, we have 1 revolution per minute or per 60 seconds. And therefore, we have omega 0, initial angular velocity, is 1 revolution divided by 60 seconds. 1 revolution, though, corresponds with 2 pi radians, and that's 0.105 radians per second. The final angular velocity, the watch second hand has stopped, so omega is equals to 0. And so now if we want to know the angular acceleration, that will be omega final minus omega initial divided by delta t. So we end up with 0 minus 0.105 radians per second divided by the time, which is 1 day. Okay, but 1 day is 24 hours, and 1 hour is 3,600 seconds. So 1 day turns out to be 86,400 seconds. So we get that alpha is equal to minus 0.122 times 10 to the minus 6 radians per second squared. Now we also want to know how many radians the second hand turned. So delta theta, or if you want theta minus theta 0, that's equal to 1/2 alpha delta t squared plus omega 0 delta t. We have 1/2 minus 1.22 times 10 to the negative, 10 to the negative 6 radians per second squared times 86,400 seconds squared plus omega 0, which is 0.105 times 86,400 seconds. Okay, you punch in the numbers and it comes out to about 4,520 radians. Okay, the next thing we'll talk about, if you have any questions, please ask the student supervising the lecture today. The next thing we'll talk about is uniform circular motion. And this is where we have constant speed around the circle. So v is the speed. It's the magnitude of the velocity. The velocity itself as a vector can't be constant because it's going around the circle. The direction keeps changing. So we consider having a circle. Let's say this is the center, and we have a small wedge. I'll make it a little bit bigger so you can see it. And let's say this is the radius, and this is the initial velocity. This is the final velocity, tangent to the circle. You'll notice if I draw the initial velocity and the final velocity, then the change in the velocity is the little piece you add to the initial velocity that gives the final velocity. Okay, you can just check that's the same thing as delta v is equal to v final minus v initial. And notice that delta v, if I'm sitting over here, delta v is pointing towards the center of the circle. Right, that's useful to know because when I calculate the acceleration is delta v over delta t. And so this points also towards the center of the circle. Okay, so this acceleration a points towards the center of the circle. Here's the center. And this is called the centripetal acceleration. Centripetal acceleration. Right. And we can say that A is equal to V squared over R is the magnitude. I'll tell you about the derivation of this formula and point towards the center of the circle. Okay, where did I pull out this formula V squared over R? I'm not going to go through the proof very carefully, but this is put in detail into the notes. I'll just show you very quickly here in the notes if you want to see more details. You have initial velocity here, initial final velocity here, you have a delta R. You look at these triangles. These are similar triangles. You have delta R, theta here, delta theta here. If we take the similar triangles, we say delta R versus R. We look at delta V over V. By similarity of the triangles, delta V over V is equal to delta R over R. And then what we can do is say, because delta V over delta V over V is equal to delta R over R, we can say delta V is equal to V delta R over R just by multiplying this thingy over there. And then the acceleration will be the limit as delta t goes to 0 of delta V over delta t. Then you plug in this formula here, and then you get V delta R over R delta t. And then you stare at it a bit and notice that delta R over delta t, that guy is going to turn into a V. And so you get V squared over R. Okay, you don't need to know this derivation, but it's just so that you realize you can derive this basic formula for the centripetal acceleration. Okay, now the next thing I want to talk about is some timing issues like the period. The period, capital T, is the time required for to go around one full circle. Okay? So you can estimate or you can calculate the period. We know the circumference of the circle, so that's actually a formula to remember. Because circumference of the circle is 2 pi r. That's the distance around. If I divide by the speed we go around, at constant speed, that gives me the time it takes to go around. And so obviously t has units. Okay, we can also talk about the frequency. Frequency, small f, is the number of cycles per second. So this is frequency, as I said, frequency. This is the period. The unit for frequency is, you'll sometimes see that written in cycles per second, and that's also called a hertz. Hertz, for Heinrich Hertz. So 1 hertz is 1 cycle per second. Okay, cycle is not really a unit, just like radian was not really a unit. Okay, the next thing we'll talk about is relating angular and linear quantities. So let's suppose I have a circle, and I have a wedge here, delta theta. Okay, and then I have this small delta s arc length, and let's say my radius is, let's call it capital R this time. We can talk about the linear velocity, and it has magnitude, known as the speed. So I call it linear velocity magnitude, but that's also called the speed. That's the magnitude of the velocity, and that will be the delta s over delta t. So we take some small time interval delta t. Now, since the arc length, delta s, we wrote down a formula that this arc length here is going to be equal to r times delta theta. Okay. then we have that v is equal to how far you go along, delta s over delta t, and that will be equal to r delta theta over delta t, and we can recognize this guy as the angular velocity. So we've derived the formula that the linear speed is equal to the angular, since the radius times the angular velocity. So linear speed is equal to the radius times angular velocity. Or if we just concentrate on the magnitudes anyways, it will be the angular speed. Okay, the very last thing I want to talk about is what happens if we have non-uniform circular motion. Okay, so we're going to break up the possibility of two different kinds of acceleration. So if we have non-uniform circular motion, we will still have this centripetal acceleration, which I will draw here, pointing towards the center of the circle. This is still true, so this is the centripetal acceleration. And this is v squared over r. Let's write capital R this time. Okay. But since v is equal to r omega, we have another formula for the centripetal acceleration. We can write ar is equal to let's do it again, v squared over r, and that's r times omega squared over r, and that becomes r times omega squared. Okay, so that's another formula for the centripetal acceleration. Ar is equal to r omega squared. But I said for non-uniform circular motion, there's actually another component. There can be a tangential acceleration. Okay? If the speed is changing with time, there can be a tangential acceleration. So let me draw again here. There can be a tangent component, tangent to the circle, at, as well as this radial acceleration, which is the centripetal acceleration. And the formula for the tangential acceleration is at is equal to the derivative of the speed with respect to time. So if the speed is not changing, there's no tangential acceleration. If it's getting faster, then the tangential acceleration is in the same direction as the velocity. If it's getting slower with time, then it goes in the opposite direction to the velocity. Okay, so now the very last formula I want to write down is because d is equal to r omega, I can write down another formula. So I can write down the tangential acceleration is equal to the time derivative of r omega dt. But r is not changing with time, so I only have d omega dt, and we recognize that as the angular acceleration. So that's r times alpha, the angular acceleration. So we have this formula for, this is all for the tangential acceleration. We have at is equal to dv dt, and we also have at is equal to r times the angular acceleration. Okay, so this is tangential acceleration. And this guy's the radius, and this is the angular acceleration. Okay, thanks for listening. I'll see everybody back on Monday.